Hello and welcome everybody to another edition of Algorand Developer Office Hours. This week I'm pleased to be joined by Jason Weathersby and Russ Festino, my colleagues here on the Algorand Developer Relations team. I'm Ryan Fox, and this week we're going to have Jason tell us a little bit about using assets along with some custom logic transfers within smart contracts. It's a pretty interesting topic. It's pretty detailed. He's going to go into it. This is a solution that'll get published tomorrow onto the developer portal at algorand.org or developers.algorand.org. I encourage you to take a look at that and make sure that you're signed up for our developer newsletter, and you'll be able to get that when it gets published. During the presentation this afternoon, where Jason is going through it, ask some questions within the questions pane of this application, and Russ and I will be there to answer them live for you. And then we'll also have Jason taking questions live at the end. So any of your development questions that you have doesn't necessarily have to be related to what Jason's going to demo. We'll answer all of your development questions as well afterwards. So with that, I'm going to turn it over to Jason.
Thanks, Ryan. Hello, everyone. This is a fairly advanced topic in Algorand, and it essentially uses some of our key features as well as using both stateless and stateful smart contracts. So I'm going to be showcasing code and running some demos to go through the code. Everything that you're going to see today is also going to be written up in a document that will be available in our solutions guide sometime tomorrow. And the source code for this is also available on our GitHub channel. I want to get started with this, but before I get started with it, I want to talk a little bit about the problem we're really trying to solve. And that is, this comes about in a lot of cases where we use a standard Algorand asset and we say, well, what if we want to put some custom logic in the situation? How do we go about doing that? So this is what this presentation is about, and we'll go ahead and start with that. All right, so to begin with, what is an Algorand asset, right? This is fairly simplistic stuff for Algorand. It's a layer 1 native token that requires no smart contract code. You can use it to build NFTs or FTs, and they take really just virtually minutes to create, and there is no on-chain code required. You can set up an administrator to mint and burn these tokens. You can freeze these tokens. You can revoke a token, and you can also delegate the authority to do any of those to someone else. And so, so assets are very configurable, and they have a lot of properties that can be manipulated in certain ways to achieve certain things. And you can even lock different capabilities within the token. So if you don't want to give people the ability to freeze a token or revoke an asset, that's easily doable as well. In addition, assets on Algorand have to be opted in by users. This prevents being spammed with unwanted assets. And you pretty much can tokenize any asset onto the Algorand blockchain, or any asset, any things like real estate, services, that type of thing. So that's the token that we're discussing today. And what typically when you want to transfer a token, say from Alice to Bob, it's a standard what we call an asset transfer transaction, and that's described on the developer documentation. I'll have links for all of this in the document tomorrow as well if you want to read through that. But it's just a standard asset transfer transaction, and it's incredibly simple to execute. All right, but what if I want this scenario where, okay, I'm going to transfer an ASA, but I want some smart contract code to run to approve that transfer or fail that transfer. And this is an issue where you go, how do I do this in Algorand? Well, that's what this presentation is about. When would you need to even do this? Well, here's a couple key use cases for this. Say you wanted to use, some type of identity management system for KYC or AML, right? So maybe as someone's transferring, you want to check not only that the user's identity for the sender and the receiver has been verified, then you can use something. You can use something like the solution I'm going to show today. Another thing is, what if you want to enforce some additional fees that are not related to the chains? The transaction fees. So maybe some basis points charged on an asset transfer, or taxes paid on a purchase if you're an online sales tool, or a real estate commission on the sale of a property. These are all different types of scenarios where what I'm going to discuss today will make sense. And basically any scenario where you need to atomically enforce a call to some logic with the transfer of an asset. That's what this whole solution is about. So stepping into a little bit more about it, how do I implement this on Algorand? Well, typically what we tell people is you can call a smart contract with the asset transfer and group them atomically. Well, and what do I mean by group atomically? I mean using Algorand's native layer 1 atomic transactions, which is you can group up to 16 transactions and they either all succeed or they all fail. The problem with this using this approach is the atomic transfers do not guarantee the enforcement. They enable it, but they don't guarantee it. So for example, here's what we look at when we talk about atomic transfers. Person A sends person B 50 algos in one transaction, and person B sends person A a concert ticket token in the second transaction. So those are grouped together. So if either one of those fails, they both fail. But what it doesn't prevent is this scenario does not prevent person B from sending person A the concert ticket, regardless of whether person A sent 50 algos or not. So essentially they can send the transaction. There's no enforcement that the code that another transaction has to be called with. So how will we get around that? I'm going to go through 3 different solutions, and on the third one is the one we will dig into and give the details in code to actually do that. So the first solution you can do is you can create the asset and then default the asset to frozen. That's one of the immutable properties of an asset. So the asset can be frozen. What does a frozen asset means? A frozen asset means no one can transfer the token from person A to person B. So that would be one way. You freeze it by default, then only unfreeze it when it's atomically called with the smart contract. That's one way you could do that. So what does that look like? Well, let's get into, I'll give you the freeze address. If you look, this is the asset properties. You have a set of immutable properties and mutable properties. The immutable properties are typically what you put in the UI if you use an Algo Explorer, or if you're using Go, you can put them in the command line, the creator, the asset name, those type of things. But one of them is default frozen. And then the other one is the immutable properties are 4 addresses that can be used to manipulate the token after it's been released to the general populace. And so one of those is called the freeze address, and it's one that allows that account. It's set to an account that can unfreeze an asset for any person or any account, or freeze or unfreeze that asset. So that's the one that we would set for this particular scenario. Okay, so say we have this freeze address. Well, this whole solution would look like this. So you freeze the freeze account, unfreezes the asset sender, let's say Alice, and unfreezes the asset receiver, say Bob, and they're both signed with a delegate signature, which is some logic that is signed by the freeze account. And then you use a stateful smart contract call for the third transaction to go check to see if it's okay to transfer the token from Alice to Bob. Say that's your identity check. And then you do the asset transfer itself. That's the fourth transaction. And then you freeze both the accounts after that all has occurred. So you can do that in one atomic operation, but it's 6 transactions. That's a pretty weighty solution for something as simple as just wanting to add some logic. So we can look at some of the problems with this. It requires a lot of transactions, and it doesn't account for fees. You have to add another transaction for the asset sender to pay the fees of the freeze account, freezing and unfreezing the 2 accounts. So that's 4 transactions that they would have to pay for. So that makes the solution even more complex. So that's a lot of transactions. And this solution will work. We've built an example that does exactly this, but this is not in my opinion, it's not an ideal solution for something like this, because it doesn't require, we're going to limit the number of transactions the best we can. So what's another solution? Another solution is to recreate the ASA in a stateful contract and don't use ASAs at all. And then we actually have an example stateful smart contract that reproduces the entire ASA standard. But the logic is, there's a lot of logic associated with it. So now you have to recreate not only that logic, but you also have to add your business logic that does the check, the identity check, or the additional checks for fees or whatever you want to, your business logic that you want to add onto a transfer. So while that solution can be done, that's not the one I chose for this particular solution that I'm working on. All right, so what's the third solution is the one that we've landed on. It's called using the callback account. Well, why would I want to use the callback account? Well, so a callback address is just another one of the mutable properties of an asset, and you can set that callback address to any address. And that callback address can remove, not only when you think of a callback, it's, oh, I take an asset from someone's account. But what is unique about Algorand Assets is when you take that asset from someone's account, you can put it in any other account, which is a nice feature. So technically, you can use the callback address to do all your transfers for you. Now, what's unique about this solution is it allows me to move an asset from any account to another, even if the asset is frozen, which is a really nice thing. So you never have to unfreeze it. You just create it default frozen and let the callback address move the token. It still allows the user to opt out of the asset by returning the tokens to the creator. That even a frozen tokens can be sent back to the creator and get out of the asset. So in this solution, first thing we would do is create the asset default frozen, use the callback address to do all the transfers. Next, we would set the callback address itself to an escrow stateless account, contract account. And what that is anytime you compile a stateless contract, it produces an Algorand address. You can actually assign that to any of the 4 properties associated with the asset, the mutable properties. So if you think about that, it's not an individual that would be doing the callback. It would be actual contract logic. So everybody's aware and realizes that there's logic associated with this, and it's not a human doing things. You can also enforce a stateless contract. In the stateless contract, you can verify that a stateful smart contract is called. The only reason you would need the one I've highlighted in green here, though, is if you needed on-chain ledger values, either global or local state. So in this particular case, you'll see as I'm going through this is an optional one. You don't have to add it. It just gives you a little bit more added capabilities if you want to use global or local state. Then the final thing you would do is you would set the manager and the freeze account to the 0 address. And that's in gold, that's just putting quote, quote, when you set them, and that locks them for eternity. So now the whole asset is controlled by logic and it's locked to never be changed. So no one can ever unfreeze that asset for the life of the asset, but no one can transfer it without going through the callback address. That's what makes the solution unique. So from a standpoint of an architecture, it kind of looks like, well, let me say one quick thing about smart contracts too. We have 2 types of contracts, stateless and stateful. Stateless, you're not using on-chain values, but they're used to approve spending transactions. Stateful are the ones that store global or local storage. And global is, oh, I got a global variable for my contract. And then for everybody who opts into that contract, I want them to have a little bit of storage where I write values that pertain to them. That's what stateful contracts do. And these are combinable and all this. But like I said, I can compile the stateless contract and it produces an Algorand address, which I set to the freeze account of the asset. All right, so from an architecture standpoint, it looks like this. Alice still sends the same transaction she would normally send. The only difference is she specifies a clawback address, and that clawback address is my stateless contract. Now, in this particular scenario, you can also optionally have the stateless contract verify that a stateful contract is called. So you could say, okay, this is a group of 2 transactions right here, 1 and 2. And then the callback address will actually transfer from Alice to Bob's account. But the transaction almost is pretty much identical as the first transaction I showed you, except you're adding the callback field, the address field, which is specified as a stateless contract. But this presents only one problem, and that's the fact that the stateless contract actually has to pay the transaction fee, not Alice. So you can then add a third contract that says, oh, a third transaction that says, did Alice pay back the transaction fee? So for the total solution, we're looking at 3 transactions. You got a call to the stateful smart contract saying, hey, is it okay to transfer this asset? And that's signed by Alice. You got a second transaction from the clawback, an asset transfer from the sender to receiver, and it's signed by the escrow logic. And then the third transaction is a transaction to pay for the second transaction's transaction fees. That's also signed by Alice. So that's the solution that I'm going to go through today. And in the way I'm going to show you this is through an example. Okay, but in this particular solution, like I said, we sum it up by saying we create the asset default frozen, use the callback address to do all transfers. Callback address is set to an escrow stateless contract, and a stateless contract verifies a call to a stateful smart contract. And then you lock up the manager and freeze accounts at the end. So just so you make sure that everybody's aware that no one can manipulate those values any longer at that point. All right. So in the example we're going to go through, I've created a leveling system with a stateful smart contract. That's why I kept that little requirement for that additional transaction to the stateful smart contract. What I want to do is create a stateful smart contract that says, okay, for a specific asset, I need to set a level. It's an integer value. It can be 1 to whatever, right, or 0 to whatever. And what it does is it says, okay, it checks every user who opts into that and says, is your level greater than or equal to the level required to transfer that asset? And if it's greater, then you can transfer the asset. If it's not, or if it's not greater than or equal to, if it's less than that, then you can't transfer the asset, nor can you receive the asset. So the smart contract not only checks the sender of the asset, but the receiver. Both must have the proper clearance level in order to transact with the asset. All right, and so what it and it stores the user's level in local state, stores the asset ID and the level required to transfer it in global state. So my smart contract basically has to support these 3 scenarios where you go. We have a set level function that the creator of the contract can set a level for a specific user. We got a clear level for clearing a user's level for a specific asset. And then another one that's called CheckLevel. And what this CheckLevel does is it allows you to check that anyone to call it, and they can check not only their level, but another's level. And the 2 levels that are being checked are the asset sender and the asset receiver. So you have to pass not only when you send the transaction, you have to pass the receiver of the asset as an additional account in the accounts array. And I'll show you how that's done shortly. These 2 accounts represent the asset sender and receiver. So my smart contract supporting basically 3 main calls: set level, clear level, and check level. I hope that makes sense. All right. So moving on, what I'm gonna in these 3 scenarios, I got Go app create, which sets the asset ID and the required level, and I also put the creator of the contract in global state too, because what I want to make sure is if they call set level or clear level, that only the creator is allowed to call those methods on the smart contract. So those are the 3 global variables that I have associated with this. These are global state variables, and the TIL approval program writes them when you create the contract. So when somebody wants to call set level, they call it and they pass a parameter that says set level, and they have passed the account that they want to set in the accounts array. And they also pass an integer of the value they want to set it to. This is only callable by the creator. It writes it into their local storage. The clear level does essentially the same thing, except it deletes the value from their local storage. Okay. The final one is the meat of the smart contract, and it's the check level. And what it's going to do is verify that it has 3 transactions, that the sender and the receiver's local storage, their level in local storage is greater than or equal to what we have in global storage for the asset. And then I have a bunch of checks in there that are standard guideline checks to make sure that you don't do things like rekeying an account or closing out an account and things like that. And you'll see when I get into the code what all that means. So as I said, this is all set in the callback address. So it verifies all 3 of the transactions and verifies the stateful app is called. That's what the stateless contract does. So it has much the same logic as the stateful contract. It just the only thing in addition it has is verifying that you also called the stateful smart contract, and it needs to know the asset ID. So those are my 2 contracts if you want to think about it that way. All right. So by the way, what I'm getting ready to show you, if you want to grab a screen grab of that, this is the GitHub location, so you can get this code what I'm getting ready to show. If you've seen me demo some of our stateful smart contracts before, you'll know that I have the same pattern when I'm working on stateful smart contracts. I always do them using Gold to begin with before I put a web front end using the SDKs, or put some other front end with the SDKs that allows me to proof the logic first before I move it to using the SDK. So that's what this particular example is going to show. In addition, and this is all available on all of these apps are available on my GitHub location that I shared earlier. But I have this, basically I'm creating a private network where I have a start net and a stop net and then a network template. It just creates a basic private network. I run that in this particular window over here. So if I just run that script, it's going to start me up a private network. So let me close that out. And the first thing I want to do is I have these 4 scripts. One creates that, then I got a set level, clear level, and a transfer. So these are basically corresponding to the functions that you saw in my PowerPoint. I'm going to go ahead and start running the create just because it takes a little bit of time, but then I'm going to walk through it and explain to you what it does. All right, so in the create while that's running, and we'll look at the output in a minute. So all I'm doing is just getting two accounts to use. Here's me getting 2 accounts. Then I create the asset ID. This is the asset that the one that's gonna be being transacted with. And you'll notice I just name it security token. I default it to frozen here. And then I send the creator account as account 1 here. This is the one account that can set the level, clear the level. Then I opt in the second account to this asset. This is all just for testing purposes. Here's where I create the app. I'm using this is my code. My approval program is called POI.teal. And for me, that was proof of identity, just in case you're wondering. I'm specifying the asset here that I created as one of my parameters for it. And the second parameter is the level required to transact with that particular token. And this is my approval program. And this is my clear program. And so once I get that app ID, I pause the program here to allow you to update the escrow. And in the escrow at the top, I specify the app ID and asset ID, the 2 applicant. That links the 2 together. All right, so going back to my create, after you hit enter, it then compiles the escrow. So I get the new escrow address. All right, and then I change the asset configuration to point the escrow, the new clawback account to this escrow for this particular asset ID. Then this is me locking out the asset so no one else can, it can never be modified. And that's all I'm doing is setting on the quote. And you can set it to 0 address with the SDKs. All right, and then the final thing I'm doing is opting in. Since I am using local storage, if I wasn't using local storage, I wouldn't have to opt into the smart contract. But I'm opting in both accounts to the smart contract because they indeed use local storage. And then I print out the global state. But I also notice here, after I change this, I actually print out the asset info. So if you look, the first thing when if I go at the end, I got an asset ID of 1 and an app ID of 3. All right, so it's just going through all these different transactions, which happen to be quite a bit, but this was basically setup logic to show how everything else runs. And by the way, I will be going through the teal code in just a moment as well. All right, so you can see here, after I cleared both the accounts, I list out the asset config, because I deleted that. And you can see that right here, that my manager address is now cleared and my freeze address is cleared, and that's the escrow account. Okay, and everybody's opt in. I've created the contract for asset ID 1, and its asset level requirement is 2, and here is the creator, which is that account 1. All right, so now that I've done that, next thing I'm going to do is go to this set level. And all I'm doing in this particular one is virtually the same thing, pull both accounts. Then I'm calling the app, which is app ID 3, and I'm specifying, this is the accounts array. I'm adding the sender of the asset, who's eventually going to send the asset to the accounts array, and I'm setting their level to 2. And then I'm calling it same call again for the second account and setting their level to 2 as well. This will give them the approval to transact in that asset, both of them. So I'll run both of those, run that real quick. All right, all right. So those two transactions got approved. So right now, both of those have a level 2. Now, instead of clearing the level, I'm going to do just the transfer. And the transfer logic's a little bit more complicated because I'm using an atomic. But let me explain it. All right. So here's the 3 transactions I discussed earlier. Okay. So the first one is a call to the Stateful Smart Contract. It says check the level of this whoever sends this transaction plus this account's level. So think about the one who sends this call is the sender, eventually going to be the asset sender. And the first one in the app accounts array is the receiver of that asset. And so I'm sending it from account 1, the first account, and checking account 2. So this would be Alice and that would be Bob in this particular case. Now I'm writing the transaction out because I'm going to do this atomically. Then I do the asset send just like I would do any standard asset send, except with one exception. You notice, see this clawback address? That clawback address is set to my escrow account. So the escrow is going to be called in order to do the clawback operation. And that one's written now. And then I do a payment transaction from account 1 to the escrow to pay back the transaction fee. And I'm assuming it's going to be 1,000 micro algos. So I write that transaction to a file. All 3 of those are written out, they're unsigned and written to a file. Then just use this cat command to combine all 3 of those into one, and then use the clerk group command to group all 3 of those transactions. Well, then you have to split them apart after you've grouped them. So I use the split command and sign each one of them individually. First one is being signed by first account. Last one is being signed by the first account. The middle one, notice, is being signed by a program, and I'm specifying the callback escrow here. So this is the logic that's actually signing that transaction. Then I combine all the signed transactions back into one transaction, and I send this to the network. So if I run transfer, okay, it writes them all out, splits them, signs them, and now they've submitted, and they just got issued, and it should just take a moment to, yep, all 3 of them got committed. So you can see here, committed, committed, committed. All 3 transactions committed. So my logic worked. As a way of proving that out, I'm going to do clear level, which is the same thing as set level, except that you don't have to pass a level. All you do is pass the clear command in the account you want to clear. And I clear both accounts. So let me do that. I mean, I could have done those atomically too, and they'd have been done at the same time, be a lot faster. All right, then the last thing, all right, so now I'm going to rerun that transfer that you saw earlier, and let's see if they get approved. You notice it says rejected by approval program. If you see that, that means a stateful smart contract denied the transaction, not the escrow, but the approval program. If it says a by approval program, then you know it's your stateful contract that failed. So let me show you another thing while I'm here. This is what I do when I'm testing whether, when I'm building my smart contracts, did I do things right? Well, you notice I got in these shell scripts, and you can look at them in source. I'll just comment this out, and I'm using the debug. So my pathing will be different than yours, so you'll have to change your pathing a little bit, but it's just /debug. It'll be in your binary directory, and I'm just debugging it, passing the name of the till program, and I'm using this dry run dump command, and that's documented on the website. You can do a dump, pass that to the debugger, and then you can actually debug what went wrong. So let me save that and rerun that. Okay, so now the debugger's running. You have to open up the Chrome Inspector, and if you just type in Chrome Inspect / inspect, this will come up. You can hit inspect, and now I'm sitting in my smart contract. And as you can see, the smart contract, to do the whole contract, is 307 lines of code. And there's quite a bit of comments in here as well. So I'm going to explain the individual pieces of this code, and then we'll walk through why this particular one failed. This is the creation logic right here. This is when I first created that account, and you can see here it checks that the application ID is 0. If it's 0, then you know this is the first time this application has been called and it's being created. Then you can look at the number of arguments. I'm making sure there's 2 arguments. And then all I'm doing is writing who the creator is to global. So that's at global put. The creator is the transaction sender. The asset ID, which is argument 1, B to I, make sure it converts it to an integer. Put that in asset ID. And then the asset level. And then I put it all in there and I return. That's the creation part of the logic. If it's not creating it, we have the life cycle of a stateful smart contract, and I can just jump to the section. All this is loops, branching sections to jump to the proper section of code to handle what you're trying to do. Like if you're trying to opt in or close out or update the application or delete the application, right? But the main one that all the logic in is this NoOp. And think of NoOp as basically just a call to the stateful smart contract, a generic call. When you go goal app call. All right, so if I go to NoOp, let me just bounce through a little bit of this because we're not in creation, so let's step through this a little bit. All right, so it's not creation, so I jump down to not creation, then it's going to go, is this a NoOp? If it's a NoOp, it's going to jump to handle NoOp, which is what it just did here. This is a standard call. First thing I'm going to check is the number of arguments between 1 and 2, because I have SetLevel, clear, and CheckLevel, and so they either take 1 or 2 arguments depending on which one you're looking at. So, and we should be good there. So let me put a breakpoint here. I'm going to run it up to here. Once it gets past this, then I can do these 3, check the actual method I'm trying to call. In the case, it's either SetLevel, clear, or CheckLevel. In this case, it was CheckLevel, so it's going to jump down to CheckLevel. And I'll show you where that's at in a minute. The SetLevel is fairly simple. All it does is take the creator, and this right here takes the first account in the accounts array and sets the accreditation level to your second argument. Your first argument is the string SetLevel. The second argument is the integer value you want to set that level, and that's the byte that I'm storing, and that's being stored in local storage. So that when I put int1 there, that means the first person in the accounts array. All right, so clears does the same thing, except it just clears uses an app local delete to delete that variable. All right, then we jump down to CheckLevel, and this is the meat of the stateful smart contract. It checks that there's 3 transactions. The first one should be a stateful transaction call. That's what this does. The second one should be an asset transfer. That's what that does. The third one should be a payment transaction. That's what that section does. And this one, this little call here just verifies that I'm currently in transaction 0, which is the stateful smart contract call. Now all this section of code, this is the boilerplate stuff that we tell you to put in almost all of them unless you need to use one of these features. So this just says, okay, make sure that no transactions are rekeying, no accounts being closed, no assets are being closed out. That's all that section of code does. And then we get into the actual checking of each one of the transactions, and you'll see what I'm doing here. So the first thing I want to do is, okay, I want to verify that, get the asset ID from the global and store this in a local variable just so I can quickly reference it later. And this is scratch space. So by the way, when you're stepping through the debugger, make sure you use the stack right here, because that's ultimately what will determine whether you're successful or not. What you want this value to be at the end is having 1 positive value on it. Any more than 1, it'll fail, or a value of 0 on the stack will fail as well. So what you want is 1 positive value. All right, so I'm loading I'm just doing a global get that we stored when we created it, and that gives me a asset ID of 1. That's what's on the stack. I'm storing that in scratch space. You'll see, I'll load it back up later. All right, so the first thing I want to do is vet the first transaction. So I want to check that, that the transaction, the person who sent the first transaction is also the person who sent the third transaction. The person who sent the first transaction is also the asset sender in the asset transfer transaction. So that just verifies that we got all the right parties involved in this. And this sets to make sure that we're actually calling this particular stateful smart contract. So that's the first transaction I've vetted. The second one, I'm vetting that the first account in the accounts array for the first transaction is actually the asset receiver. And then this load 11, that when I stored the asset ID earlier, I'm loading it back up and verifying the asset transfer is actually the asset ID I'm expecting to be transferred. Then the third thing, then I'm going to vet the third one, which says I want the second transaction sender to be equal to the the second transaction's receiver, i.e., this is the callback address. This is the account 1 or Alice in this particular case. No, this is the escrow, excuse me. This is the escrow, this is the Alice account. So want to make sure that she is actually paying the fee back into the escrow. And then this is how I check to make sure that the fee is correct. I check the third transaction's amount and check it against the fee that was paid in the second transaction. It's got to be greater than or equal to. All right, now we get to the actual level check. So all I'm doing here is when this is the sender of the transaction. Notice I got int 0. That says, okay, it's technically in the accounts array, but it's the first element in the accounts array, and that's always defaults to the sender. So you'll see, okay, I want to look up the application ID. The application ID I currently have, this is the application ID, and then I'm looking for the cred level variable in the local state. And when I do app local get ex, it returns 2 values. The first value just says 1 or 0. Was it there? If it wasn't there, then it automatically fails. And then if it is there, I want to make sure that this is me getting the asset level from the global variable, and make sure that it's greater than and equal to that. If it's not, fail. Then I repeat the same exact logic, except I change this. Int 1 now, which is the first account in the accounts array, which means the sender. And then finally, if all of that's successful, then I return 1. So let's see why this failed. So we're up here in this logic. We'll just step through this a little bit. All right, so it looks like, we'll see if we get through the first transaction. All right, so checking here, we got a 1 on the stack. I'm doing a BZ failed. BZ says if that's a 0, jump to failed. If it's a 1, then keep going. All right, so first transaction vetted properly. Now I'm checking all the properties of the second transaction. Same difference. There's a 1 there, no BZ, so I should step over that. Now I'm going to vet the third transaction. Here's the fee. Here's the fees. The fee for the transaction, the third transaction amount is greater than or equal to the fee from the second transaction. So when those are ended, that's a 1. So when I do a BZ, it actually clears the stack, but moves on. So everything is good up to this point. So now we get to the actual accreditation level check. So when I step through this, I go int 0. That's the sender. All right, there's the application ID is 3. That's the app ID for this particular stateful smart contract, and I'm looking up accreditation level as the variable. Now I do the app local get. It typically returns 2 values, and the first one says, oh guess what? It's a 0, meaning this variable does not exist for this user for this stateful smart contract. So in this particular case, this BZ failed is going to jump down the fail. And I load an int 0 on the stack and return. I technically could have popped one of those off and just left the 1 on there. I didn't really need to load up the int 1 in that particular case. All right, and so then I play it out, and then that's why you know it failed. And so that's one nice thing about using dry run dump is I can literally debug any contract this way and quickly figure out what is going on, what did I do wrong in my contract. All right, so we'll highlight that out. All right, so from a standpoint of, and then I can recall SetLevel again and reset the levels back to 2. Okay, and then rerun the transfer. And you will see that they will all get committed again, unless I mess up my logic. All right, yep, so they all committed here. Committed. All right, so that's the gist of the approval program. The escrow account is virtually the same logic. You can see the same logic is associated with the escrow account, right? The only difference is, but it's only 116 lines of code, and the only difference is I am setting the application ID and the asset ID. The reason being is because I checked these down further in the code because I want to tie this escrow to that particular stateful smart contract. And like I said earlier, if you did not want to use global or local state, you don't need POITL. All you need is the clawback escrow, and you can put everybody your logic in this and check it in here. So you don't really need to do stateful contract. And if you have a different type of logic. Now, let's say, for example, you were doing a commission project where anytime an asset got moved, someone had to be paid a commission. Then you don't need a stateful smart contract. You can check it all in the stateless contract. But the reason I used it for this example is because I wanted to store their online level. So it essentially allows us, this whole project is created so a company can come in and be a KYC provider and offer this contract to anybody, and they will vet the folks that are associated with it and be able to set their level and control that contract for a specific asset at an asset level. So that makes it very stateful indeed, right? So, but in the case where a commission was going to be paid or something like that, probably don't need that. All you probably do need is this stateless contract. And then you simplify it to basically 2 transactions. One transaction from the escrow to do the clawback, and then one transaction to pay the transaction fee. And that's essentially all there is to it. And then, oh, last thing, the clear, you'll notice the clear is just int1 return, nothing special there. So this whole example is available, like I said, on the GitHub site. Let's go back to the presentation. Is available in this location if you want to grab a shot of it. Please join the Discord channel. That's the best place to get answers to questions. We're on it all the time. You can also use the forums. Nice thing about using the forums is they're very searchable later. Make sure you use one of those 2 areas to get your questions answered. The developer portal is located at developer.algorand.org. Our Algorand's GitHub is github.com/Algorand. Underneath there's the smart contracts examples. Just look for smart contracts, and you'll see I have a bunch of examples that we've already placed in there, and we'll be adding more to it. And make sure you sign up for future developer office hours. Do we have any questions?
Radek asked a good question that has to do with the opcodes TXN versus GTXN. Oh. And how do you know the context of the if you're just using TXN, that is in the context of this app,
So TXN always represents whatever application called that particular whatever transaction called that contract. So when you see in my code, if I go when I look at if I look at TXN group index, that says this current transaction, what's its group index? It'll be 0 in this particular case because I'm in the stateful smart contract, which happened to be the first call. So TXN represents the current transaction you're processing. You can reference any transaction in an atomic group using GTXN. So GTNX0 is the same thing as TXN in this particular case. GTNX1 is the second transaction in a group. GTNX2 is the third transaction in a group. So this is why I specifically put this one. That check in there to say, okay, am I absolutely group index 0 here? I wanted to verify that I was actually GTNX 0, and I should be in this particular case. So that's a way of verifying.
In this group transaction, that means that the first transaction is the application call transaction.
That's exactly right. And I also did this check too, so it gives you a little bit more. These are the types of transactions I expect. This doesn't say, hey, this is called my particular transaction I did. It says my particular stateful smart contract. It could be any stateful smart contract. That's why I did further checks down below. Pleasure presenting today, and thank you for attending.